Hey there. In this video, we're going to start looking at power series solutions to higher order differential equations. Specifically in this section, we're looking at solutions about what we call ordinary points. So let's start by talking about what it means to be an ordinary or a singular point. If I have a differential equation in standard form, such as this one, y double prime plus p of x y prime plus q of xy equals 0, then x naught is an ordinary point of the differential equation if the coefficients p of x and q of x are analytic at x equals 0. And if they're not ordinary points, then they're singular points. So you're either one or the other. And just a refresher on what it means to be analytic. A function is analytic at a point if it can be written as a convergent power series around that point x naught. So in a neighborhood around it, not just at that single point. And so some common ones we work with, polynomials, they're analytic at every x value. So we don't have any issues with those. We like looking at differential equations with polynomial coefficients in this unit. And rational functions are analytic within their domain. So that means whenever their denominator is not equal to 0, then they're rational functions. So let's say I started out with a differential equation that wasn't in standard form, where I have a leading coefficient on my y double prime of a2 of x. If I was going to put this into standard form, I would divide all the coefficients by a2, which would give me a p of x of, say, a1 over a2 and q of x of a naught over a2. And so these would only be analytic when a2 is not equal to 0. And so something to keep in mind when you're looking at these kinds of problems. If a2 equals 0, then that's a point that would be a singular point. So if x naught is an ordinary point if a2 is not equal to 0, and x naught is a singular point if a2 at that value is equal to 0. Okay, so the next thing we're going to talk about is, well, how do we know when we have a solution, a power series solution to a differential equation? So it turns out if x naught is an ordinary point of the differential equation, then there exists exactly two linearly independent solutions in the form of a power series around x naught. So y would equal the sum from n equals 0 to infinity of cn times x minus x naught to the n. Now, most of the time when we're doing this, we're letting x naught equal 0, but that's not the only place we're limited to that value. Okay, so the process that we're going to use to find power series solutions to homogeneous differential equations is going to be, first, we're going to make sure we're dealing with an ordinary point. Usually we're going to just go with x naught equals 0 unless you're given some other value specifically. And then we assume that we have a power series solution. So much like we did when we were dealing with characteristics equations, we said let y equal e to a power of x. So here we're going to say let y equal this power series. And then we'll take this power series and its derivatives and plug them into the differential equation. So we're going to end up with a lot of series inside this differential equation. And then we want to align all those sums so that they all have the same power of x. So for instance, we want them all to be x to the k. We don't want any to be like x to the k plus 1 or k minus 2 or something like that. And then we'll probably need to re-index the sums so they all have the same starting value. And then we can condense them all down to a single sum. And re-indexing them often requires us to pull out some initial terms from series that start earlier. So we're looking for that series that starts the latest, and then anything else you need to pull out so it starts at that latest value. Once we get everything condensed down to a single sum, we can form a recurrence relation because the identity property for series tells me that all my CNs, they have to add up to 0 since this is a homogeneous equation. So we're going to use that to create a recurrence relation that defines the terms of the series, the coefficients of the series. And then we're going to compute the first few terms and put all that together to form our solutions. Okay, so that's the general strategy. Let's put it into practice with an example. So here I have y double prime plus x squared y prime plus 3xy equals 0. And so I'm going to solve this, find its power series solutions. So we're going to assume, since we weren't giving any x naught values, x is 0, and these are polynomial coefficients in standard form, so I don't have an issue. 0x equals 0 is an ordinary point here. So I'm going to let y equal the sum from n equals 0 to infinity of cn times x to the n. And then I'll take its derivatives. I need the first and second derivative to substitute into this differential equation. So I'm just doing power rule. So I get cn n times x to the n minus 1 for the first derivative, and that one's now starting at 1 instead of 0. And the second derivative is going to start at 2, and I get cn times n minus 1 times x to the n minus 2 by just doing power rule. Okay, so all three of these sums are going to go into the series. Don't forget about the x squared and the 3x coefficients. And so I get this long equation. These can get a little overwhelming. Take your time, look at the details as you go through these. So I have my first derivative series plus x squared times, the second derivative, then I have plus x squared times the first derivative, plus 3x times the original solution y. And so the first thing I'm going to do is I'm going to take the x squared and the 3x, I'm going to push those into the sum and combine them with the powers of x that I have in my sum. So x squared times x to the n minus 1 becomes x to the n plus 1. And then x times x to the n becomes x to the n plus 1. Okay, so the next thing I want to do is I want to get all the powers of x to match. Okay, we want to do this before you change the starting values of your sums because it will mess things up if you do it in the reverse order. So the first series has an x to the n minus 2, and the other two have an x to the n plus 1. So in each one of these, I'm going to replace the exponent with k. So for the first series, k is going to equal n minus 2. It's whatever the exponent is on your x, that's what k is going to equal. And then for the other two, x will equal n plus 1, since that is the exponent on those values. And so I'm going to swap all these out. This is going to change the starting value, which is why I wanted to do this first. And it's going to change everywhere there's an n showing up in all three of these series, they're going to change. So if k equals n minus 2, then that means that n equals k plus 2. So wherever there's an n, I'll replace it with k plus 2. So the first series becomes the sum as k equals 0 to infinity of c sub k plus 2 times k plus 2. And then n minus 1 becomes k plus 1 if I swap out the n for k plus 2. And then times x to the k. Okay. On to the second one. I'm going to do the same thing. Okay, here k equals n plus 1, so that means n is going to equal k minus 1 if I just solve this little equation for n. That's why I always take the time to write out those definitions so I don't make a mistake here. Okay, so that means that this series is going to start at k equals 2. And really, I'm just plugging the starting value, which was n equals 1, in for n. So k equals n plus 1, so that's 1 plus 1 gives me a starting value of 2 now. And then the expression inside of the series becomes c k minus 1 times x to the k. And the last one, same substitution. This time my starting value was 0, so now it's going to be 0 plus 1. So we start at k equals 1. And then the expression is 3c k minus 1 times x to the k. And all of this adds up to 0 still. Okay, so we've made a lot of progress by messing around with this. I now have 3 series all with an x to the k. They all have a different starting value though, and so the next thing I need to do is I need to re-index them so that they all have the same starting index value. The one that starts the latest is the middle one at k equals 2, and so I want to change the other two to start at the same value. I can't make k equals 2 really start earlier without affecting my x to the k. So the best way to fix this is to take out some values from the other two sums. So for the first one, k starts at 0. So I need to pull out the k equals 0 term and the k equals 1 term. And then this series will start at 2. And for the third one that starts at 1, well, I just need to pull out that first one so that it will start as 2 as well. And I'm just going to take these, pull them out of the sums. They're going to end up out in front of everything. We're not going to forget about them, but we do need to separate them from the sums. So if I plug in 0 to the first one, I'm going to get 2c2. And if I plug in 1, I'll get 6c3x. Okay, and so now my series that starts at k equals 2. The middle one, I don't have to do anything to. The third one, I'm going to pull out the first term. So 3c0 x is going to be the first term that pulls out. And now all three sums start at k equals 2. Okay, let's clear the board and see what we do next. So took all three of those terms that I pulled out of the sums, threw them out in front of all the sums, and now I'm going to be able to combine these three series together. So the summation notation is going to be the same for all of them. And I'm even going to factor out the x to the k from all three of the terms that I'm going to get here. So it looks something like this. So I've got my 2c2 plus 6c3x plus 3c0x out front. And then I have a series from k equals 2 to infinity of all of those expressions. So c sub k plus 2 times k plus 2 times k plus 1 plus k minus 1 times c sub k minus 1 plus 3 c k minus 1, all times the x to the k. And all of this still adds up to 0. Okay, so looking at that mess inside of my sum, I notice I do have two terms that are a c sub k minus 1. So I can clean this up a little bit and combine those two a little bit. So I'm really just factoring out a ck minus 1. And I'm going to end up with a k plus 2. If I do k minus 1 plus 3, that'll give me a k plus 2 there. So it cleans it up a little bit. We want to make this as simple as possible because it is pretty complex. I also looked at the terms out front and I had two x terms. So I'm going to factor the x out of those and combine those. And we're doing this because at the end of the day, what I really care about is finding all of these c's. And so that's the next step now that I've combined everything into a single sum. I've simplified it as much as I can. And now I'm going to start pulling these things out. All of these things have to add up to 0, which means the coefficients have to add up to 0. So if I look on the left, I have a 2c2. It doesn't have any like terms anywhere in any of this. So 2c2 has to equal 0, which means that c2 equals 0 in this case. Same thing with the next set, 6c3 plus 3c0 also has to add up to 0. It's the only x terms in the sum, so the coefficients have to cancel each other out. And so I'm going to solve this for the highest coefficient here. So the c3 is the higher between the c3 and the c0. So I'm going to subtract 3c0 and divide by 6 to get a definition for c3. So c3 equals negative 1/2 c0. You're always going to go with the higher one. That includes with the coefficient inside of my series. So the third equation I can solve here is I can take the coefficient on my xk, and that also has to all add up to 0. And so the higher index here is the ck plus 2. So I'm going to solve this for that value. And so that means I'm going to subtract the ck minus 1 term over and then divide by the k plus 2 times k plus 1. So I get some k plus 2s that cancel out, and I end up with ck plus 2 equals negative 1 over k plus 1 times ck minus 1. And this is my recurrence relation. Well, actually, all three of these statements at the bottom together are the recurrence relation. And this last piece, well, this one starts at k equals 2 because that is when my power series started. Okay, so I pulled out those terms out front, and then I have a series that starts at k equals 2. So this formula kicks in starting at k equals 2. Okay, so the next step, really we're almost to the end here, is I want to start plugging in values of k for this system and find some actual coefficients to put on my x to the k. Now the thing to remember is all of the coefficients at the end of the day, whatever their subscript is, so if I have c sub 3, then that's going to be multiplied by an x to the k. Okay, so that one will be multiplied by x to the third. So something to keep in mind as we formulate that final example. It's easy to get kind of lost and forget what am I multiplying each of these coefficients by? Well, they're all getting multiplied by an x to the k. Okay, so we've got our recursive relationship here where c2 equals 0, c3 equals negative 1/2 c0, and then I have my expression for ck plus 2. Notice that in all of this, the earliest coefficient I have is c2, And I don't have a definition for C naught, so that's an arbitrary value. If I wanted to get a concrete particular solution, I can assume a value for C naught. C1 is also not defined by anything in my recursive relation because C2 is the earliest. CK plus 2, well, that starts at k equals 0, which means the first value it's going to give me is C4. So C naught and C1 are arbitrary coefficients that if I wanted to find a particular solution, I could pick values for them. So oftentimes we'd say, well, what we get one solution when C naught equals 1 and a second solution when C naught equals 0 or C1 equals 0, and then switch it. For now, we're just going to keep them as unknown though. Okay, so let's start with the first value of k that we can plug into that last piece. So k equals 2 means that C4 is going to equal negative 1/3 C1. And all I did was plug in 2 for k everywhere in that formula. Okay, and C1, again, that's one of our arbitrary constants, so we can't simplify that any further. So then we'll go on to k equals 3. So this gives me C5, which is going to be negative 1/4 times C2. Now, if you remember though, C2 is 0, so C5 is going to be 0. And then we move on to the next one. K equals 4 will give me C6, which is going to be negative 1/5 C3. And oh wait, we know what C3 is. C3 is negative 1/2 C naught. So I can actually replace C3 with negative 1/2 C naught and get C6 is 1/10 C naught. So what I'm trying to do here is get all of my coefficients to be in terms of one of my two arbitrary coefficients, either C naught or C1. So if we keep going, in k equals 5, I get negative 1/6 C4, and then I can use the definition of C4, which was negative 1/3 C1, to give me C7 equals 1/18 C1. And I'll keep going. This might be a good place to pause and try and work these out on your own. C8 is going to end up being 0. C9 will give me negative 1/80 times C naught. And I'll do one more. When k equals 8, I get C10 equals negative 162 over C1. Okay, so I went, several in, especially because I got a lot of 0 coefficients, and I want at least a few non-zero coefficients for my final solution. So to piece this all together, my general solution is going to be C naught times my first solution plus C1 times my second solution, since those were my two arbitrary constants. So really what I'm doing is I'm taking all my coefficients, I'm going to multiply them by their power of x, and I'm going to factor out the C naught and the C1 from each one of these. So for the first one, well, I got C naught itself was my first one, which I don't even have on the screen, but it does exist as my first arbitrary constant. So I've got a 1 to placehold that one. The next coefficient I got with the C naught in it was for C3, which was negative 1/2 C naught. So I get 1 minus, now I have 1/2, and it's x to the third because this is my C3. So I'm matching up the subscript on my coefficient with the power of the x here. And then I keep searching, where's my next C naught? When k equals 4, I got 1/10 C naught, and that was my C6. So the next term is 1/10 x to the 6th. And then the last C naught that I got was C9 with the negative 1/80 C naught. So that gives me a minus 1/80 x to the 9th. And then I just do a plus ... to indicate that this is going to continue. If we luck out and we have a nice pattern that we can write as a sum, that's great. We're not going to even try that with this one today, though. And then I'll do the same thing for the other half. So picking out all my C1s. So I had a C1, so my first coefficient is 1. And then I just start finding, okay, C4 had a C1 in it, so that's minus 1/3 x to the 4th. C7 has a C1 in it, so that's plus 1/18 x to the 7th. And then the last one was C10, so minus 1/162 x to the 10th, and then plus ... and so on. And so my two solutions are in the parentheses, and I could I get those from this by saying, well, if C naught equals 0 and C1 equals 0, that gives me the second one. And if C naught equals 1 and C1 equals 0, then that gives me the first one. So those are my two solutions. Here's the linear combination to give me the general solution.